Hey guys, Mr. B here. In this video, we're going to be going over the chapter 10.2 notes on the relative age of rocks. So in this section, we're going to be talking about the law of superposition, how geologists use that to determine the relative age of rocks, as well as how our index fossils used. So here we go. So remember that when we are looking at rocks, sedimentary rocks are usually the types that we're going to be looking at when it comes to relative age. Now, it doesn't mean that igneous rocks and things aren't useful either, but sedimentary rocks are oftentimes the ones that are going to contain fossils, as well as they make nice layers very well. So we have two ways to express age of rocks and fossils. There's relative age, and relative age is usually an age in comparison to other ages of rocks. So a lot of students get this confused and they think that relative age means like it's an approximate or it's an estimate about age, and that's wrong. Okay, relative age is just simply older or younger, and that's it. Okay, when you are looking at the age of something relative to something else, it's older or younger, there are no numbers. Okay, this is the key thing to know. Relative age does not include numbers at all. It's not an estimate, it's not a guess, it's not an approximation. There's no numbers at all. It's just saying that's older than that or that's younger than that. That's it. Okay? Absolute age, that's when we start putting years on a rock, like how old it is, how many years old it is. And even then, this is usually an approximate or estimate in years. So we typically, when we look at the age of a rock or a fossil, geologists typically do not just go, oh yeah, that's, 1,235,000 years old. No. Usually they're guessing, like a range. It's usually a time scale. So they'll say, yeah, this fossil or this rock is probably somewhere between 100 million years old and 110 million years old. Okay, they don't go down to exact numbers like that. So the main thing to know is absolute age has numbers on it, relative age does not. Okay, don't get those two confused. All right, so what is the law of superposition and how does that relate to the position of rock layers? So as sediment usually forms, sedimentary rocks, they're going to be deposited in layers with some on top and then of course as you go down. And so over time the sediment hardens, becomes rock, and the law of superposition is what we can use to determine the relative age of these rock layers as we go from top to bottom. Basically the law of superposition says that in rock layers that are horizontal, the oldest layer is on the bottom and the youngest layer is on the top. Okay, so older layers are put down first, younger layers are put on top. I like to think of this as the law of pancakes. Sounds silly, but it's easy to remember, and here's why. When your parents or your mom or dad make you pancakes on the weekend, usually they have a plate, right? And they put the pancakes on this plate and they stack them on top of each other. And you and your siblings come and grab them and put them on your plate. You know that the hottest, freshest, newest, youngest pancakes are the ones that are right on top, right? And the oldest pancakes, the ones that came off the griddle first, that have been sitting there for a while and might be kind of cooled down by now, are the ones on the bottom of the plate. So usually, of course, you're going to grab the pancakes right on the top because they're nice and fresh and hot. They're young, right? They're nice and good. The ones that are on the bottom of the plate might have been there for a while. They might have cooled down a little bit. Maybe not quite as hot or as warm. So you don't usually grab them, right? They're older. Okay? Easy way to remember it. Just a simple thing. All right. We're not going to be going over the questions here. I have a video of me going over those. So if you want to watch that, you can. We're going to keep on moving to talk about information. All right. So how do we determine the relative age of rocks? So there are other clues besides just rock layers that help us to determine the age of the rocks, okay? Rock layers are certainly helpful, but over time, rock layers get shifted around. There's rock slides, there's earthquakes, there's erosion, all kinds of stuff can happen, and rock layers, as nice and neat as we want them to be, are not usually just found in layers like this, okay? There's all kinds of stuff that's happened between them. So to determine relative age, we also look at extrusions, intrusions of igneous rock, faults, and gaps in the geologic record. We'll go into these each specifically and kind of talk about what they mean, okay? So igneous rock is formed when magma or lava hardens. Magma is usually molten material beneath the Earth's surface, and lava is molten material on top of the surface, okay? So lava that hardens on the surface is what we call an extrusion. So it's basically where magma pushes its way up through the rock. It gets to the surface and it pools on top of the ground on the surface. So it's now on the exterior. We call that an extrusion. And that is usually going to be younger than all the rock that's below it. Okay, so if there's an extrusion sitting on top of the surface, that is younger than all the rock below it because it had to push its way up through all that rock. That rock had to be there first in order for that to push its way through there. Okay. An intrusion is magma that cools and hardens into a mass that's pushed into other bodies of rock. It's usually going to be underground. So an intrusion is where igneous rock will push its way up through other rock layers, but it won't break the surface. So it's underground, okay? And that intrusion is always going to be younger than all of the rock layers that it cuts through, okay? So this is also called the law of cross-cutting or the principle of cross-cutting. And it's not labeled here in the notes, but any rock layers that it cuts across, it will be younger than all of those layers. Okay, there's some practice problems, I think, in a sheet and some examples and videos that kind of go over that a little bit too. So anyway, all right, moving on. Other clues come from studying faults. A fault is usually a break in Earth's crust. So a fault line is where two plates usually meet and they shift. It's a lot of times where like earthquakes will happen. And so usually rock will move on each side of the fault. The fault is always going to be younger than the rock it cuts through. Okay, so if you have rock layers and that they're shifted like this, right? Some might be up or down. That fault that caused those rock layers to shift will be younger than the rock layers themselves because the rock layers had to be there first in order for that fault to shift them. So here's some pictures of some examples of intrusions and faults. So in this picture on the left, we have an image of an intrusion. Okay, so this rock layer that's pushed its way up through this other rock. This is igneous. This is an igneous intrusion. It is going to be younger than all the rock that it's cutting through because this rock had to be there first in order for that intrusion to make its way through. Whereas in the image on the right, we have a fault line. We can see it. There's these kind of white bands of rock. And there's this kind of big, thick white band here on the left of the fault line and a big, thick white band here on the right. And there's kind of a thinner band of white up above and a thinner band of white up on the right. We can see that those layers have kind of shifted where these white bands are no longer lined up anymore. It kind of seems like, you know, the one on the right of the fault is up higher and the one on the left is down below. So that also tells us that this fault happened after these rock layers were already put down. So this fault layer is younger than the rock layers themselves. All right. So other than looking at intrusions, extrusions, and fault lines, other times there can be gaps in the rock layers themselves or gaps in what we call the geologic record. Again, this is due to erosion, all kinds of stuff that happens over time where rock layers just don't stay the same way forever. So usually sedimentary rock layers are not always going to be complete. Deposition, that means that, you know, deposits of other rock layers will slowly build upon layer of sedimentary rock. Some of these layers can erode away, which expose older rock surface before then new layers get deposited on top of those again. And so the surface where new rock layers meet at a much older rock surface beneath them is what we call an unconformity. It's usually a gap in the geologic record. So it looks something like this. So imagine that we have a bunch of rock layers, okay, in the top left here. Over time, as the ground gets pushed up and stuff like that, folding can occur and we kind of get waves in the rock layers. And then maybe we have kind of like a mound here, which then gets eroded due to water or wind or whatever. And so these rock layers, which were originally up near the surface, are now mostly gone. And then, of course, new rock layers get laid down on top of those ones. And so now we have what we call an unconformity. This is where we have all these rock layers that were complete, but they got kind of erased, or part of them got erased away, and then new rock layers get put down. So this can also give us ideas about which rock layers were there first, because we know that these rock layers here that were folded had to have been eroded in order for these rock layers to be sitting on top. Okay, so what we call an unconformity. This can also help us to determine the order in which rock layers can occur. All right, last thing here we're going to talk about are fossils and how we can use those to find and date rocks. So certain fossils we call index fossils are very helpful in matching rock layers. So an index fossil is basically a fossil where the organism is going to be widely distributed, but it only existed for a relatively brief amount of time. Okay? So an index fossil, again, is a fossil where you can find it in multiple layers, but the fossil itself of that organism was only around for a very short period of time. And so the reason why it's helpful is because if that organism was only alive for a short period of time and we find it in multiple rock layers, then we know that those rock layers must be the same age, because that organism is found in all of them and it wasn't around for very long, right? So all those rock layers had to have been around at the same time. So they're very useful in helping us tell the relative ages of rock layers in which that they occur, because of the fact that we can kind of use them to match up rock layers that might not look like they're in the same location because maybe they've shifted and things like that. But index fossils will help give us those clues. So here is an example of some different rock layers. And if we look at these, I might ask you, looking at the different fossils here, which might be a good fossil to use as an index fossil? Now, if we look in layer A, we see this kind of butterfly-looking fossil, and I'm sure it's supposed to be a shell or something. But we find it in layer A, we find it in layer B, and we find it in layer C. Not a good index fossil, because we find it in all these different layers, and these probably all happened over a very long period of time. And so this organism probably lived for a very long period of time. Therefore, it's not a good fossil to use as an index fossil. Also in layer B, we find this kind of horn-looking shell, which we find in layer B, we find in layer C, and layer D. Again, not a good index fossil. We find it in too many places and over a too long period of time. The trilobite fossil, though, in layer A, so this one that kind of looks like a sow bug or a box elder bug, that would be a good index fossil. We only find it in layer A. It's not found in any other layers, which means that organism probably only lived for a very brief amount of time or a very short or a certain time period, and it's found all in these rock layers, which means these rock layers are probably all the same age. In layer C, we find this ammonite shell, this kind of spiral-looking shell. Also, again, only found here in layer C. We don't find it in other layers. That can help us to match up that these rock layers are the same age. And we can even notice, too, that it looks like some erosion and things have happened because in location 1, we have 4 layers. In location 2, layer D is no longer there anymore. Location 3, we only have layer A. And in location 4, we've got layer A, layer C, and layer D. But layer B, it looks like it has been eroded. So if we use the law of superposition, we might think that layer B with these two and layer C, we might think these are all the same age because they're all at the same level. But in reality, we know that this layer C here in location 4 is actually younger than these layers here in location 1 and 2 because it has a fossil in it that is found in layers that are above layer B in layers 1 and layer 2, or in location 1 and location 2. Because this ammonite fossil can be used as an index fossil to tell us that these 3 layers here in location 1, 2, and 4 at layer C are all the same age. Okay, so this is where index fossils can really be helpful. Okay, so hopefully that helped you with some relative age stuff. That is all there is for this section of notes. In the next video, we'll be going over the practice questions. All right, that's it for now, guys. I'll see you in the next video.